Hi, this is Adam Griffin with the first video for this week. So this is going to be problem 23.1, which is the assigned problem. It's the first problem on Mastering Physics. So there's two parts to this, and it's going to deal with the charge of point charges and the electrical fields of point charges. So part A, so it gives us this figure right here where we have 2 point charges, both positively charged to 3 nanocoulombs, and they have this distance here labeled R, and then a point right here, which is R distance away from the midpoint between the 2 point charges. So part A asks, what is the strength of the electric field at the point of the dot? And it says that R equals 6.7 centimeters. So a couple things to think about before we start. A positively charged point charge is going to have an electrical field that points outwards. So at the point charge, it's going to be the forces pushed like away from wherever these 2 point charges are. So to find the strength of the electric field, we have to first figure out the strength of the electric field from just one of the point charges. So to do that, we have our K constant, which we'll write out in full with 1 over 4 pi, and then this little variable right here, times the charge of our particle divided by the distance between the point and the charged particle squared. So first, because we don't know this diagonal distance right here, we only know the horizontal and vertical, we'll find that really quick, and we do that with the Pythagorean theorem. And we get that R1 is equal to the square root of 0.067 squared plus 0.067 squared meters, because it's 6.7 centimeters. And since when we plug into the equation the radius squared, we can just get rid of this square root sign, and R1 squared just becomes the term inside of the square root, which is equal to 8.98 times 10 to the negative 3 meters. So when we plug that into this equation, and we use K, 8.99 times 10 to the 9th for this, and then we have our charge, 3 nanocoulombs, which is equal to 3 times 10 to the negative 9th coulombs. We plug those all in, and we get a charge of 3,000 newtons per coulomb. And we also need to know that the y components, so the up and down components of these 2 charges cancel out because they're the exact same charge and the exact same distance. So any electric field that is pushing on this point right here is going to be canceled out by the electric field of the other point. So all we have to do is figure out the combined x components of the electrical fields from both points. So to do that, we just take, we know that because these are equal, the x, sorry, a little bit of a brain freeze. The x component of the electric field is equal for both point charges. So all we have to do, because these 2 sides are the exact same length, this is 45 degrees. So we multiply this by cosine of 45 degrees, and we get 2,124 newtons per coulomb. And that's for just one of the charges. So in order to find the combined, the net electric field, we just multiply that times 2. So because these are equal, it is just times 2. So that is equal to 4,248 newtons per coulomb at the point. And then part B asks, what is the direction of the electrical field at the dot? And we know that since these points are pushing away, that it's going to be going to the left, only in the x direction. So the answer is horizontal to the left for part B. So that is how you do 23.1. I hope it was straightforward, and thank you.